The relations for YVA can be written in the form of sine function. In the form of sine function, we have y is equal to a sin omega t. A is amplitude. V is equal to a cos omega t. V can be written as a omega. V is equal to a omega cos omega t. V is equal to a omega cos omega t. It can be written as a omega sin 90 plus omega t. Sin 90 plus omega t, since sin 90 plus theta is equal to cos theta. So for cos omega t, we can write it as sin 90 plus omega t. Similarly, acceleration is minus a omega square sin omega t. Minus a omega square sin omega t. It can be written as a omega square sin 180 plus omega t. A omega square sin 180 plus omega t. Since sin 180 plus theta is equal to sin theta. Here we should not be get confused. Sometimes I am using A for amplitude and sometimes I am using R for amplitude. Both mean the same. Relation between phase of displacement, velocity and acceleration. The relations for displacement, velocity and acceleration are y is equal to a sin omega t, v is equal to a omega sin 90 plus omega t, and a is equal to a omega square sin 180 plus omega t. Comparing these three equations and comparing the phases, we notice that phase of y is omega t, phase of v is 90 plus omega t, phase of acceleration is 180 plus omega t. So the phase of velocity is 90 more than that of displacement. The phase of acceleration is 90 more than that of velocity, or 180 more than that of displacement. The same thing can be understood from the graphs. The first graph is the relation between y and omega t, displacement versus phase. The second graph indicates the relationship between velocity and phase. And the third graph indicates the relationship between acceleration and phase. From the first graph, what we notice is the displacement is 0 at equilibrium position when the particle starts. Then the displacement is in the positive direction. And when we take the velocity curve, we notice that the velocity is maximum at t is equal to 0 at equilibrium position, and the velocity decreases as the particle moves from equilibrium position. From the third graph, we notice that the acceleration is 0 at equilibrium position, but the acceleration becomes negative and increases as the particle moves from equilibrium position. Comparison of phase of displacement, velocity and acceleration. Comparison of phase of displacement, velocity and acceleration. In the first graph, we have shown the relation between y and omega t. It is the relation between displacement and phase. Y is taken on y-axis and omega t is taken on x-axis. It is a sine curve. In the second curve, the velocity is plotted on y-axis and phase is plotted on x-axis. On x-axis, phase is taken and on y-axis, velocity is taken. Now it is also sine curve, but the initial phase is maximum here. V is maximum initially. Then the third graph indicates the relation between acceleration and phase. The third graph indicates the relation between acceleration and phase. Here acceleration is taken on y-axis, and this relation indicates that the phase is 180 more than that of the displacement. From the graphs, what we notice is the phase of velocity is 90 more than that of displacement, and the phase of acceleration is 90 more than that of velocity and 180 more than that of displacement. General equation of motion. General equation of motion. The general equation of motion is given by y is equal to a sin omega t plus phi. Y is equal to a sin omega t plus phi. In this equation, a is amplitude, omega t plus phi is phase. Omega t plus phi is phase. Phi is known as phase constant. Phi is known as phase constant. From this equation, it is evident that the particle will not start from O when we count its motion. The position of the particle is not O when we start counting the motion of this particle. It will be at a distance. It will be at some distance from the equilibrium position. To understand this point, I have shown a point beyond O. That shows this point is the position when the time t is equal to 0. At the time t is equal to 0, the position of the particle will not be O but another point such as the point shown in the figure. To understand the concept of phase, phase, let us consider the circular motion. In the circular motion, I have shown OP0 is the position at t is equal to 0. OP0 is the position of the radius vector at time t is equal to 0. And OP is the position at time t is equal to 0. Here, omega t plus phi represents the angle from OX to OPE. That is the total angular displacement from the reference axis. But at time t is equal to 0, the position of the radius vector is OP0. It is making an angle phi with OX, the reference line. So this is initial phase or phase constant. This position, the angle subtended by OP0 with OX is phi. This is known as phase constant or initial phase. Concept of phase constant in graph. Let us observe the graph. In this graph, at the time t is equal to 0, the displacement is not 0 nor maximum. At time t is equal to 0, omega t is 0. When omega t is 0, from the graph, the displacement of the particle is not 0. It has some displacement. This displacement is indicated by the phase constant phi. By using the value of phase constant phi, we can obtain the displacement. This is the initial displacement of the particle executing simple harmonic motion when we begin counting its motion.